On August 19, 2026, scientists announced a discovery that shocked everyone paying attention to Pluto. Liquid nitrogen is actively erupting from the surface right now, not in the distant past, not millions of years ago. Right now, today, this moment, nitrogen geysers are shooting upward through cracks in frozen plains, freezing instantly in Pluto's paper-thin atmosphere, accumulating as fresh deposits on the surface. Pluto is geologically alive. For decades, we thought Pluto was a dead, frozen rock, a distant, boring world with nothing happening. No change, no activity, no life. But on August 19, 2026, that assumption shattered. Scientists studying images from NASA's New Horizons spacecraft discovered something that forced us to completely rethink what it means for a world to be geologically alive. A dwarf planet, smaller than Earth's moon, billions of kilometers from the sun, colder than any place humans have ever visited, and it's more geologically active than we ever imagined. This discovery changes everything we thought we knew about the outer solar system. It proves that life, geological life, doesn't need warmth from the sun. It doesn't need a massive internal heat source. It can happen anywhere, in the coldest, darkest, most distant places. Pluto is alive, and its story is about to blow your mind. Here's what most people don't realize. When we look up at the night sky and think about other worlds, we imagine them as static. A moon, a planet, a fixed object suspended in space. Maybe it orbits, maybe it has craters, but basically it's just sitting there, unchanging, dead. Earth is alive because we have life, because we have activity, because things grow, move, change. But what if I told you that alive doesn't mean what you think? Not biologically alive, geologically alive. A world where the landscape changes, where material moves, where processes reshape the surface, where energy from inside the planet forces material to the surface. That's what Pluto is. For over 70 years, Pluto held a special place in our solar system. It was the 9th planet, the mysterious outer world. Everything we knew about it was vague. Then in 2006, scientists reclassified Pluto. No longer a planet, now a dwarf planet, a demoted world, suddenly less important. Most people felt disappointed. Pluto lost its status. But here's what the scientists didn't tell you. Reclassifying Pluto made it more interesting scientifically. Instead of thinking of Pluto as a lone planet in the outer system, we could study it as the prototype for an entire category of worlds. Trans-Neptunian objects, icy bodies orbiting beyond the Neptune in a region called the Kuiper Belt. Thousands of them. Most of them unknown, most of them unexplored. Pluto became the key to understanding this entire population of distant, frozen worlds. Then in 2015, something changed everything. NASA's New Horizons, a spacecraft, finally reached Pluto. After 9 years of traveling through the solar system, after billions of kilometers of journey, this little spacecraft approached the most distant world humanity had ever studied up close. And what scientists saw shocked them completely. The images arrived on Earth on July 14, 2015, high-resolution photographs of Pluto's surface. The first time we'd ever seen Pluto in detail, and Pluto was nothing like we expected. It wasn't a barren, cratered, dead rock. Pluto had mountains made of water ice, towering 5 kilometers high. Pluto had vast plains of frozen nitrogen, impossibly smooth and young-looking. Pluto had canyons, ridges, evidence of geological process. Pluto looked alive. The most striking feature was a region shaped like a giant heart. Scientists named it Sputnik Planitia, roughly 1,000 kilometers across, filled with frozen nitrogen. So perfectly smooth, it seemed impossible. Impact craters should cover old surfaces. Billions of years of asteroid impacts should create a landscape of destruction. But Sputnik Planitia had almost no craters. The geology looked fresh, the landscape looked actively modified, the frozen plain looked like it was changing right now. For 11 years, scientists have analyzed those New Horizons images obsessively. Every photon, every pixel, every detail, looking for clues, looking for evidence of activity. And in August 2026, they found it. Liquid nitrogen is rising through cracks in Sputnik Planitia. Actively, right now. This is cryovolcanism, the frozen equivalent of volcanic activity on Earth, but on Pluto, on a dwarf planet smaller than Earth's moon, billions of kilometers away. This changes everything about what we understand regarding how planetary geology works in the outer solar system. This is the moment science reveals something we didn't know about our cosmic neighborhood. This is the moment we realize our assumptions were wrong. Let me explain how scientists discovered this. It starts with a question that seemed simple on the surface. Why is a Sputnik Planitia so smooth? On Earth, we have lava plains, ancient flows of lava that cooled and hardened. They're relatively smooth, but they still have texture, still have variations. Sputnik Planitia is different. It's almost unnaturally smooth. The smoothness suggested something profound. The plain was either very young geologically, or it was actively resurfacing itself. If the surface was billions of years old, like most of Pluto's crust, it should be covered in impact craters. But it wasn't. It was pristine. That pristine condition meant either, one, something was constantly erasing those craters, or two, the surface was being continuously rebuilt. Scientists called this the Sputnik Planitia problem. How could a surface on such a cold, distant world be so young-looking? Then they discovered the cracks. Looking at high-resolution images, scientists identified deep fissures cutting through a Sputnik Planitia, not random cracks, systematic patterns. And around some of these cracks, they found material that shouldn't be there. Deposits, accumulations, fresh material on the surface. The pattern suggested something was forcing material UP from below. Something was pushing nitrogen through those cracks. And it was happening recently, possibly actively. This triggered a theoretical question. What could provide the energy? Pluto is tiny, about 2,400 kilometers in diameter. It's smaller than Earth's moon. It orbits so far from the sun that it receives virtually no solar heating. The surface temperature is about negative 240 degrees Celsius. That's 240 degrees below the freezing point of water. It's the coldest place we've ever studied in detail. In such an environment, where does energy come from? Scientists proposed several theories. First theory, internal radioactive heat. Pluto formed from material that contained radioactive elements. Uranium, thorium. These decay slowly, releasing heat over billions of years. That internal radioactive decay could generate enough heat to 1. Keep material below the surface liquid. 2. Create pressure that forces material upward through cracks. Think of it like this. Deep below Pluto's frozen crust, there's a layer where nitrogen exists as liquid nitrogen. At Pluto's temperatures, nitrogen melts at negative 210 degrees Celsius. So while the surface is negative 240 degrees, just below the surface could be warmer. Warm enough for nitrogen to be liquid. That liquid nitrogen is under pressure. Pressure builds, pressure increases. When a crack forms in the crust, that pressure forces the liquid nitrogen upward. It erupts like a geyser. In Pluto's thin atmosphere, it freezes instantly. It accumulates as fresh deposits. That's cryovolcanism. But there's another energy source scientists proposed: tidal heating. You see, Pluto isn't alone. Pluto has a moon named Charon. Charon is huge, about half Pluto's size. They orbit each other in a gravitational dance. The gravitational interaction between Pluto and Charon creates a stress. Stress causes friction. Friction generates heat. This process is called tidal heating. On Jupiter's moon, Io, tidal heating from Jupiter's gravity is so intense that it creates active volcanoes with temperatures exceeding 1,000 degrees Celsius. On Saturn's moon, Enceladus, tidal heating keeps subsurface water liquid, creating water geysers that spray into space. On Pluto, tidal heating from Charon's gravity combined with internal radioactive decay could generate enough heat to keep nitrogen liquid below the surface, could create enough pressure to force geysers through cracks. The combination of both processes, radioactive decay and tidal heating, is probably what's happening on Pluto. Scientists analyzed the geyser deposits and found they were nitrogen-rich. Exactly what you'd expect if frozen nitrogen was erupting from below. They analyzed the crack patterns and found they aligned with the stresses created by Pluto-Charon gravitational interaction. Everything pointed to one conclusion: Pluto is geologically active. Nitrogen geysers are real. They're happening right now. The landscape is actively changing. Pluto isn't dead. Pluto is alive with geological process. This is the moment everything changes. For 100 years, since Clive Tombaugh discovered Pluto in 1930, we assumed that distant, small, cold worlds were geologically dead. We thought you needed 3 things for a world to be geologically active. 1, size. You needed a massive planet to retain internal heat. 2, youth. You needed relatively recent formation to still have internal energy. 3, heat. You needed either solar heating or recent internal cooling. Pluto violates all 3 assumptions. Pluto is small, smaller than Earth's moon. Pluto is ancient. It formed 4.5 billion years ago. Pluto is far from the sun. It receives almost no solar heating. By every logic we possessed, Pluto should be geologically dead, a frozen, inactive, unchanging ball of ice. But it's not. It's actively changing. Nitrogen geysers are erupting from its surface. The landscape is actively being reshaped. When I say this changes everything, I mean it literally. This forces us to rethink the criteria for geological activity. This tells us that activity doesn't require what we thought. It doesn't require a massive size. It doesn't require recent formation. It doesn't require solar heating. It requires something else. It requires internal energy sources, radioactive decay, tidal heating, combined with processes that can transport that energy to the surface. And those conditions exist in places we never looked carefully, in the coldest, most distant places, in the smallest worlds, in the places we thought were dead. Here's what makes this profoundly important. When New Horizons flew past Pluto in 2015, scientists expected to see a geologically dead world. Instead, they found evidence of ongoing activity. That evidence sat in datasets for 11 years. 11 years. It took until 2026 for scientists to analyze those images carefully enough to recognize what they were seeing. Nitrogen deposits that shouldn't be there. Cracks that were actively forming. Patterns that only made sense if geysers were happening. And they're probably happening right now. At this exact moment, while I'm explaining this to you, nitrogen geysers might be erupting from Pluto's surface, 5 kilometers up, freezing in the atmosphere, falling back as ice, transforming the landscape continuously. This is an ancient history. This isn't something that happened a billion years ago. This is happening now. Think about that. We live on a planet with an active core. Earth has earthquakes, volcanoes, plate tectonics. We assumed that geological activity required that kind of massive energy. But Pluto shows us something different. Pluto shows us that geological process happens at the coldest, most extreme scales. Nitrogen at negative 240 degrees Celsius. Pressure building underground, cracks in the crust, eruptions. This is as alien as geology gets. This is as different from Earth as you can possibly imagine. And yet it's fundamentally the same process. Energy, pressure, release, surface change. The mechanism is universal. The details differ wildly. But the principle is the same. Wherever there's internal energy and a path to the surface, geology happens. Wherever there's pressure and a crack, eruptions occur. Wherever there's geological process, worlds change. Pluto changes. Pluto is alive, not biologically, geologically. The landscape is different today than it was yesterday. The surface is different this moment than it was last moment, because nitrogen geysers are actively modifying it. This is the revelation that changes everything. Not that Pluto is interesting, but that our understanding of which worlds can be geologically interesting was fundamentally incomplete. We thought we understood planetary geology. We thought we knew the rules. Pluto proves we were wrong. And if we're wrong about Pluto, what else are we wrong about? What other worlds that we assumed were dead are actually alive? That's the real question this discovery raises. Let me expand this. If Pluto can have active geology despite being small, ancient, and distant, then the outer solar system is far more dynamic than we thought. Consider Neptune's moon Triton. Triton is similar to Pluto in many ways. It's small, it's icy, it's in the cold outer solar system. In 1989, Voyager 2 flew past Triton and photographed its surface. Scientists saw something shocking at the time: nitrogen geysers. Triton has nitrogen geysers erupting from its surface. We've known this for almost 40 years, but we didn't understand why. Triton seemed too small, too distant, too cold to have that kind of activity. Now with the Pluto discovery, the Triton geysers make sense. If Pluto has them, Triton having them is expected. Consider Saturn's moon Enceladus. Enceladus is even more dramatically active. Not nitrogen geysers, but water geysers, massive fountains of liquid water erupting from beneath the icy crust and spraying into space. We discovered these geysers in 2005. Since then, we've learned that Enceladus has a subsurface ocean, liquid water, thousands of kilometers wide, beneath a thin, icy shell. That ocean is kept liquid by tidal heating from Saturn's gravity, the same mechanism that works on Pluto. Consider Jupiter's moon Europa. Europa is covered in ice. Beneath that ice is a subsurface ocean. We've never directly observed eruptions from Europa, but the evidence suggests activity. We believe Europa's ocean is kept liquid by tidal heating from Jupiter's gravity. Tidal heating. Again, the same mechanism as Pluto and Enceladus. What we're seeing is a pattern. In the outer solar system, tidal heating combined with internal radioactive decay can keep subsurface material liquid. On Triton and Pluto, that liquid is nitrogen. On Enceladus and Europa, it's water. In both cases, that liquid can find pathways to the surface. It erupts as geysers. The landscape changes. These worlds are alive with geological process. Here's what this means. The outer solar system is not a graveyard of dead, frozen worlds. It's a realm of dynamic, changing, geologically active bodies. It's alive. Not with biological life, we don't know about that, but with geological process. With energy and activity and change, this changes how we should explore the solar system. Right now, NASA has plans for a Pluto orbiter, a mission that would reach Pluto in the mid-2030s. Instead of flying past like New Horizons, the Pluto orbiter would orbit the dwarf planet. It would monitor Pluto for years. Scientists could watch geysers erupt. They could measure the frequency of eruptions. They could understand the mechanics of cryovolcanism in detail. They could study how tidal heating and radioactive decay interact. But the Pluto orbiter isn't just about Pluto. It's about understanding an entire class of worlds. Because if Pluto has active geysers, what about Triton? What about Eris and Makemake and Haumea? What about the hundreds of other trans-Neptunian objects in the Kuiper belt? How many of them have active geology? How many are alive with geological process? We don't know. We barely looked. And that's the profound implication of this discovery. We've explored 0.1% of the ocean. We've mapped 0.1% of the asteroid belt. We've studied 0.1% of the Kuiper belt. And we've only sent one spacecraft to study it in detail. New Horizons, one spacecraft, to an entire region containing thousands of worlds. The Pluto orbiter mission is planned for the 2030s. That's 10 years away. For 10 years, Pluto will remain barely studied. Its geysers will continue to erupt. Its landscape will continue to change, and we'll be mostly watching from afar, analyzing old data. Think about the implication. Right now, at this moment, there's a dwarf planet billions of kilometers away, experiencing geological transformation. Nitrogen fountains are shooting upward. The crust is shifting, the landscape is being reshaped, and we're not there to see it. We won't be there for at least a decade. By then the landscape could be significantly different. This brings me to a philosophical point. For centuries, we believed Earth was unique, the only active planet, the only world where things changed and evolved and transformed. Slowly, we've learned that assumption was wrong. Venus has a thick atmosphere and active volcanism. Mars once had liquid water and geological activity. Jupiter's moon Io has active volcanoes with temperatures exceeding 1,000 degrees. Saturn's moon Enceladus has water geysers. We've learned that geological activity is common in the solar system, but we've still held to the idea that the coldest, most distant places were dead. Pluto proves that assumption wrong too. The coldest place we've ever studied has active geology. That's the final assumption shattered. Here's what Pluto tells us. Geological activity doesn't require what we thought. It doesn't require planetary mass. It doesn't require solar heating. It doesn't require recent formation. It requires energy and a mechanism to express that energy. Those conditions exist in many more places than we realized, which means many more worlds are alive with geological process, which means the solar system is far more dynamic, far more active, far more interesting than our previous understanding suggested. The outer solar system is alive, and Pluto is the proof. This discovery is the beginning of understanding that proof. The true revolution in our understanding of the outer solar system hasn't happened yet. It's coming. When the Pluto orbiter arrives, when we can study these worlds continuously, when we can map their geology in detail, when we can finally understand the mechanisms that keep these distant worlds alive, That's when the real transformation in our understanding will occur. But it starts here, with a dwarf planet smaller than Earth's moon, billions of kilometers away, where nitrogen geysers prove that even in the coldest, most distant places, geology is alive and changing. The universe is far more dynamic than we assumed. And every time we look carefully, we discover we were wrong. That's the real wonder of science, the continuous discovery that the universe is a stranger, more active, more alive than our previous understanding allowed. Pluto is just the latest example. But it's a powerful one, because if Pluto, small, distant, ancient, can be geologically alive, then what else are we wrong about? What other assumptions do we hold that are waiting to be shattered? What other discoveries are waiting in the outer solar system, just waiting for us to look carefully? That's the real question Pluto's geysers raise. So here's what we know. Pluto isn't the dead, frozen rock we thought it was. It's geologically alive. Nitrogen geysers are actively erupting from its surface. The landscape is continuously changing. Tidal heating from its moon cairn, combined with internal radioactive decay, keeps material below the surface warm enough to be liquid. When that liquid nitrogen finds cracks, it erupts. The universe revealed itself to be more dynamic than our assumptions allowed. This happens again and again in science. We think we understand the rules. Then we look more carefully and realize the rules are different. Einstein did this with gravity and a space-time. We thought gravity was a force pulling objects together. Einstein showed us it was actually the curvature of a space-time. The rules were different. Darwin did this with life. We thought species were fixed and unchanging. Darwin showed us life evolves and adapts. The rules were different. And now scientists studying Pluto have done it again. We thought small, distant, ancient worlds were geologically dead. Pluto shows us they can be alive with geological process. The rules are different. The outer solar system isn't a graveyard, it's alive, not with the kind of life we have on Earth, but with geological life, with process and change and energy and transformation, with worlds that are actively becoming different from what they were yesterday. That's what Pluto teaches us. And that's why this discovery matters. Not because Pluto is particularly important, not because nitrogen geysers are particularly interesting in isolation, but because Pluto shows us that our understanding of the universe was incomplete. And incomplete understanding means unexplored possibility. If we were wrong about Pluto, what else are we wrong about? That question drives science forward. If you didn't know that Pluto has active geysers, if this discovery changed how you think about the outer solar system, if you realized that even the coldest, most distant places are geologically alive, then subscribe for weekly documentaries about space mysteries, ocean discoveries, and facts that change how you see the universe. Like this video, if Pluto's geysers blew your mind. And in the comments, tell me which outer solar system world you want to explore next. Thanks for watching. We'll see you next time on Mind the Snap.